All right. Welcome to Third International Hydrogen Energy Congress and Exhibition Session E. We have planning started 6:35 p.m. We have planning finish the session 8:20 p.m. We have one invited speaker and five speakers, five participants from another countries and universities. We will start with Professor Dr. Asif Ali KOCAELI. I would like to give information about Professor Dr. Asif Ali KOCAELI. He is currently working as professor and chairman, Department of Polymer and Process Engineering, University of Engineering and Technology, Lahore, Pakistan. He did his PhD from University of Auckland, New Zealand, in Chemical and Material Engineering in 2011. Professor KOCAELI's research interests include membranes, electrochemical independence spectroscopy, intrinsically conducting polymers, and polymer rheology and processing. Earlier, Professor KOCAELI has worked in various national and international organizations, including National Fertilizer Corporation, National International Engineering and Scientific Commission, and as a consultant for Fisher and Paykel Appliance, New Zealand, where he carried out various projects included melt, flow, behavior, and life estimation of polycarbon resin. Currently leading a group of postgraduate students at the department, he is involved in researching on polymeric membranes for distillation, electrodialysis, and perforation application. Associated with other groups, he helps in studying electrochemical behavior of sensors, functional films, and nanoparticles using electrochemical independence spectroscopy. Jointly with Professor Irfan's groups at Gazi University, he started developing novel proton exchange membrane and GDL-based intrinsically conducting polymers for improved proton exchange membrane fuel cell performance. He has a good liaison with other active membrane research groups, including Tashio University and Qian Jitong University from China. I think the professor is ready. We can see his presentation. Okay, dear professor, you can start.
Thank you very much. Am I being heard? Can you hear me?
Yes.
Thank you. Thank you for such nice introduction. Good afternoon, everybody. And today I will give you an overview of that very powerful technique, electrochemical impedance spectroscopy, with its particular application to fuel cell performance evaluation. Right. My presentation will consist of three major parts. A brief introduction of the fuel cell. How do we look, we electrochemical people look on these fuel cells as an electrochemical system. And then a brief overview and introduction of electrochemical impedance spectroscopy. And in the last, the small work that we have done here in collaboration with Professor Irfan Stoop from Ghazi University, covering this electrochemical impedance spectroscopy. Excuse me. So we can see that we are running short of the conventional fuels that we had up to 18th century in the name of fossil fuels. And now these are being depleted very rapidly. And also another aspect is the environmental pollution and ever increasing awareness towards that environmental pollution, mainly in terms of CO2 emission. So these are the issues that cleaner and renewable technologies, including fuel cell technology. Number two, if we see the efficiency versus power output rating or the regime, we see the fuel cells at the top as compared to diesel, gasoline, and steam turbines. So fuel cells are efficient as well, cleaner. There are various types of fuel cells, and mainly my group or myself and my collaborating people, we work on this PMFC, polymer electrolyte fuel cell, where an ion exchange membrane is involved, that is polymer electrolyte membrane is involved there. What does it do? It converts chemical energy into electrical energy. Yes, we all know, environmental friendly, high efficiency, no liquid electrolyte involved. What we have gases. Water is produced in hydrogen fuel cell as a result of the reaction, but this is not the major electrolyte. Yes, it's pollution free, up to 90% reduction as compared to conventional fuels. And then operates at low pressure, means it's a quick startup. We don't have to build up the pressure to get it started. Right. This how how does it look like? Very basic and very common schematics that we have here. We have actually two gas diffusion layer, schematically I'm talking about, coupled with catalyst layer and a membrane, hydrogen ion exchange membrane that is sandwiched between these two electrodes. One side we feed hydrogen as a fuel, oxygen comes from air, and oxidation reduction that these two reactions take place at both catalyst, electrodes, and what we have electrochemical energy as output and the water as the product. Okay. Application of fuel cells and particularly PMFCs, again, we have portable energy sources as the application, transportation system, getting very common day by day, and then in mobiles, in laptops, in many other systems, a potential application in communication systems. So this is very interesting, again, but basic diagram where we have fuels at the outermost periphery. We start with hydrogen, methanol, biofuels, petrol, and then the applications here. Types of fuel cells, PM is here, solid oxide fuel cell is there, uh, ethanol fuel cell, DMFC, that is there. And application wise, we have transport, there we have road, sea, air, stationary, where we have residential, industrial application. So it's a whole spectrum that we can cover. It's not only up to the automotive application that is usually understood or conceived. It has much more broad application spectrum, fuel cells. We all know what we have. We have anode and cathode and polymer membrane as an solid electrolyte that allows the passage of hydrogen but restricts the passage of electrons. There shouldn't be any short circuit, electronic short circuit there. Uh, so it allows the flow of electrons through external wire or the circuit connecting two electrodes, anode and cathode. Then we have three boundary reactions at catalyst layer and membrane. We have platinum-based catalyst layer, then GDL, porous gas diffusion layer for water management, few gaskets, bipolar plates, these sort of things that we have commonly in fuel cell. Anode, what we have by construction, it is catalyst layer plus GDL, where this catalyst converts hydrogen, actually oxidizes hydrogen into hydrogen ion. On cathode, again, we have catalyst and GDL. And here we have reduction in ORR reaction, oxygen reduction reaction, that is converting this oxygen into water. Assembly wise, we can see this is membrane electrode assembly, MEA, where we have membranes sandwiched between two GDLs coupled with catalyst layer. And this is the whole assembly of, including these bipolar plates, whole assembly of the fuel cell, very basic thing. Yes, coming towards EIS, electrochemical impedance spectroscopy. It's a very powerful diagnostic and modeling tool for fuel cell. I'll explain in brief. I'll try to. What we do, we measure voltage losses or potential losses, and these correspond to all the dynamic processes that are dynamic processes involving charge transfer and charge transport within the cell. These may include kinetic losses, ohmic losses, and actual mass transfer resistances or losses. So as a result of these three restrictive processes, we have voltage losses, and we measure those, and then we interpret the processes which are taking place within the electrochemical system. Here we are talking about fuel cell. So it is an experimental method that separates and quantifies different sources of polarization. That is very interesting. It doesn't only measure, quantify, but it has the ability to distinguish the, by nature, distinguish these losses and these polarization sources. Also, we can have in situ and ex situ measurements or diagnosis. How? I'll give you a few examples. Starting with the very basics of this impedance. What is impedance? Impedance, corresponds to a resistance. When it is a pure resistor, uh, this box is there, then R is equal to V over I, voltage over current. We all know this. But when it is impure, part of capacitance is involved along with this resistor, then this resistance is usually called impedance, right? How we start building on this? If we apply the sinusoidal signal here in this diagram, E, uh, we measure against this input signal, we measure the output current. And for pure resistance, coming back to left-hand side, the pure resistance, this output I is totally in phase with the input signal, that is our potential or voltage E. But in capacitance, that is totally out of phase to the input signal. And for a mixed element, that is, we have some phase shift. Again, coming back to this right-hand side diagram. So this phase shift is there. This is the basis of what we talk about impedance analysis. Moving ahead, we have three common elements: resistor, where we have, instead of Z, we have this R. So Z impedance is R for pure resistor. For capacitor, uh, the Z is related with the C, and it is again the impedance of the capacitor depends on the frequency. Omega is the frequency here. Then opposite to capacitor, what we have is inductor, where the output leads as compared to, or leads to, the input signal. So this is again impedance is related to the inductance L, again depending upon the omega. I'll explain later on how to cope with these things. Here, if we see on left hand side an inductor L, uh, resistor, what we have a real axis, and on inductor we have imaginary positive axis part. But for this RC element, we have this real for resistor and capacitance as the negative imaginary axis. More precisely here in below, when we have this resistor in series with this inductor, the total impedance is addition of individual impedances, that is R, and impedance comes from the inductor, and this is a representation on these two real and imaginary axes. This is for capacitance representation, where this capacitant, this blue arrow is that is ZC. It is from this capacitance. Again, if we move on to right hand side, so we can combine these elements and we can enjoy the response representation of those responses. For example, on right hand side, I will draw your attention to this bottom portion where we have RC and C resistance and the capacitant connected in series. So this is how we build up on these elements, and how do we calculate the amplitude of the resultant impedance ZC mod, and phi, that is the phase angle. Similarly here, inductor, the response lags 90%, sorry, leads 90% to the input signal, and capacitance, it lags to 90%. When we measure this complex impedance with the imaginary and real component, we have two options of the representation. The first one is Nyquist, that is more common. So the impedance data are presented in most commonly in Nyquist form, where we have imaginary axis and we have real axis, and this is on left hand side we have typical R and capacitance, resistance and capacitance parallel combination plot. That is a typical semicircle. Uh, on real axis, on high end side, on left hand side, that is high frequency end side, we have this where this semicircle touches the real axis, we have R omega, and on right hand side where we have very low frequencies, the intercept is R omega plus the polarization resistance of this R that is in parallel with this. Uh, for a typical polymer electrolyte fuel cell, membrane fuel cell, we have these three semicircles, complete or half semicircles, Nyquist plot, and we can distinguish different processes going on based on each semicircle represent a time constant process. So on higher frequency, we can go for ohmic or electronic processes, fast processes. On the extreme low frequency and what we have mass transfer or diffusional processes. And in between we have electrode, we can assign the electrode activity. This is a Bode plot, another type of representation of this data where we have frequency as explicit variable. So this is actually impedance versus frequency and impedance, sorry, phase angle versus frequency plots, right? So these are the characteristics of Nyquist and Bode plots that we have decided. Very interesting when we talk about equivalent circuits. So Randall circuit is one of the most common that we encounter in modeling this. What we do, we take the response either in the Nyquist or Bode form, and then we try to interpret that response, first fitting that response with various equivalent circuit. Equivalent circuit means combination of resistor, capacitance. We'll talk about later about the constant phase element, a type of capacitance. And then we try to correlate these elements with the physical processes that are taking place within the electrochemical system, the system that is our fuel cell. So particularly if we get, for example, let me go in this way. If we get this semicircle that is shown here on right top, and bottom is the Bode plot of the same electrochemical system, the response. Uh, we can fit this, we can fit this circuit, a Randall circuit that is shown on left hand side. That is RS, a resistor in series with a combination, parallel combination of another resistors and the capacitor, right? So that can be fit to this type of semicircle easily. And this part 0 to 100, that is RS, and this semicircle, it is a combination of this CDL, double layer capacitance. So there are various sources of capacitance here. Usually it is a double layer capacitance, or and then the charge transfer resistance, that is RCT, uh, represented this by this semicircle. If there are diffusional processes which are involved as well, then we can include this left-hand side. We can include another diffusional element, that is Warburg element, W, another type of capacitance there. And what is the result of this right-hand side? A semicircle, and then a 45-degree rise uh, in the curve that is represented by this W, right, or modeled by this. So we have different elements. We have resistance to a resistor that represents ion transport or electron transport, then charge transfer process resistance. So resistor, a resistor can represent any of those processes, depends upon the frequency at which it is resolved. Then we have capacitors and inductors, which are mainly for space charge polarization regions such as electrochemical double layer and adsorption or absorption, desorption processes there. So we have various elements here: resistor, look at this table, inductor, capacitance, CPE, constant phase element, a type of capacitance, a distributed capacitance, you can see, uh, inhomogeneous capacitance. This is CPE, constant phase element, right? And Warburg is another type of capacitance, half capacitance, you can see, right? Further to this, again, conventionally, when we have this Randall circuit, left-hand side diagram, when we have this Randall circuit, we have semicircle as the output, or the when we try to fit this semicircle data with the Randall, we can do it easily. But here on left-hand side, when we have this series element, we can have this is actually Nyquist plot, and then Bode plot. In you can see in Nyquist it is a straight line for series resistor and capacitors, but here for parallel resistor and capacitor we have this semicircle. That is very interesting. But when we have what is a CPE, a constant phase element, that is in homogeneous capacitance like this shown here. And for this, what we have this equation that is our impedance depends on the an index n or exponent n. For pure capacitance, this n is 1, where Q is the capacitance. Q is the capacitance. You can replace Q with the C here, right? So when Q is C, when n is equal to 1, this Z is pure capacitor. But for distributed capacitor, there are more than one time distribution. So this n ranges from 0 to 1. So what is the result? Result is that we have, you can see here this uh, red curve is for pure capacitor, and for this purple is when we have this. So as a result is that when we have a pure capacitor, we have a perfect semicircle. But when we have this constant phase element, since the time constants are being distributed, what we have a depressed, distorted semicircle. There are many indications, applications again of studying this or applying this electrochemical impedance. We can have corrosion, electrodeposition, battery studies using these sort of plots in fuel cells. Look at this. A typical schematic, uh, GDL, diffusion layer and node, another GDL, cathode, sandwiched membrane, electrolyte, polymer electrolyte membrane. We can represent this system through these equivalent circuits. R coupled with the parallel capacitance and the Warburg or diffusional resistance. These represent in combination of GDL and a node. Similarly on other side, and this electrolyte membrane, it is represented by resistance R omega. And what the output that we get this three uh, time constant processes, two semicircle, one Warburg here, and this circuit can be fitted well to this data and then correlated to these three layers. This is how we start. Sensitivity is there. Look at this. This is body plot of.
Dear Professor, I am sorry, I don't want to interrupt your presentation. You have 3 minutes more. Thank you.
Okay, I will try to wind it up. So sensitivity is there, where we can have a body plot for hydrogen oxidation reaction, oxygen reduction reaction at low frequency, very low, 10 millihertz. We have diffusional processes. So this is actually a different current density. So the curves are well resolved for different current densities for fuel cell. Similarly here, this is another representation for different DC potential. Polarization potential on impedance of Nefion. So again, we have sensitivity. We represent this behavior with this equivalent circuit, and as we change the potential, what we have a change in the shape and also the magnitude or the size of the semicircles there. Another example of a spectra of 0.5 volt for MEA at low and high temperature, LTP and HTP at different, you see activation times, 3, 5, 8, 9 hours. And also in this bottom diagram, what we have changing temperature. This is LTP and this is HTP. So sensitivity is great for electrochemical impedance spectroscopy while studying the here what we have done, we conducted a small study of EIS using PVA, SPVA, satellite membranes provided by Professor Irfan's group from Ghazi University. This is an interaction between PVA, sulfonated PVA and saprolite that we proposed conditions, experimental condition, and these are the results. We studied these PMs, polymer electrolyte membranes, for 2% this solid saprolite content, and we fit this circuit here. We got this response, and we fit this circuit. Fitting was excellent, and we could get the results, and then 5%. What we have seen that heterogeneity increases. Yes, of course, as the loading increases the heterogeneity of the membranes in terms of electrochemical processes. These increase, and resistance is reduced. The various resistances that are involved for these electrochemical charge transfer processes, these reduced by increasing this solid content, and many other features that we can see. We can have a long discussion on these results in comparison. A few good references from where I took the help, and thank you very much for being with me, and your questions are welcome, please.
Okay, thank you, Professor Dr. Asif Ali Kausar. It's really nice topic. Do you have any question? I am asking to dear participant. If you have a question, please write down the chat part of the Zoom. I can ask to Professor Dr. Asif Ali Kausar.
Yes.
Okay, I think somebody has a question. Kemal Ershen. If you have question, could you please write down from the chat session? I don't wanna lose the time. Okay. I'm still waiting. Okay, nobody write the question. I would like to thanks again, Professor Dr. Asif Ali Kausar. Thank you so much again.
My pleasure. Thank you very much for inviting me for this session. So nice of you. Thank you.
Thank you so much. Okay, another presenter is, I will tell to name. Okay, just a second. Another presenter is Osman Yağız Akman from Gebze Technical University. His presenter title is Cost Models of Different Types of Tubular Solid Oxide Fuel Cell, a Trade-off Study Between material cost and cell performance, and its effect and stack cost and multi-scale mass production projections. If you are ready, you can share your present. Dear Osman Yağız Akduman, are you here?
Yeah, here. Sorry.
Okay. If you are ready, could you please share your presentation?
Yes. In a second. Sorry. I'm trying to.
All right.
I'm new to Zoom. This is the first time for me. Yeah. Share screen. Yeah. Can you see the screen now?
Okay. Yes, we can see your screen. Could you please the full screen button in the presentation mode?
Yeah.
Could you please enlarge, please, if it's possible? Okay.
So it is in full screen,
Thank
right?
you.
Because I'm right now using 2 screens on my own here. So you're using the,
yes.
You're seeing just the
presentation. It's full screen. You can start. You can.
Okay. Yeah, first of all, I would like to welcome you all. My name is Osman Yağız Akduman. I work at Gebze Technical University as a PhD student. Today I will talk about cost models of different types of tubular solid oxide fuel cells, and it's a trade-off study between material cost and cell performances. First of all, we should start with the model parameters, I guess. We choose 3 different production scale per year, and we're using cells with a length of 5.5 centimeters and a diameter of 3 millimeters. It has an active area of 4.7 approximately. And you're also seeing the materials are used in here. Probably you wouldn't know what the extent of YSC means, uterus stabilized zirconia, and Scandia series stabilized zirconia for SCCZ, and the other one is hafnium erbium stabilized bismuth. The same is lanthanum strontium manganite. So I think we can skip this part. These are the devices or the equipments we use here at Gebze Technical University. There are different devices with different scales and the necessary information like mean power consumption, capacity, and the operating days, etc. Electricity cost is based on the at the industrial rate in Turkey, also the gross minimum wage. Working hours per week is assumed to be 40 hours. These are the cell types. There are 2 base anode side electrolytes, which is YSC and SCZ, and there is an additional second electrolyte for both these types of cells. So in total, we have 4 types. I showed you planar type schematics, but in real life, we're working with tubular type. So you're seeing an example of micrographs here. These are the cell specifications. Right below, you see a double layer electrolyte cell. I just wanted to show you how it looks like. And these are the performance parameters of the cells. As you can see, cell type 4 is the best, but also the most expensive, and we will talk about this later. This is the simple process flow. I didn't want to confuse you with big and confusing images flow charts. So basically, we extrude an anode support and coat it with AFL and sinter it. And then the first layer of electrolytes is also coated and sintered along. And then cathode functional layer and cathode coating is conducted and then sintered together. Additionally, for cells with double layer electrolytes, there's an electrolyte coating, and this electrolyte coating is sintered along with the cathode function layer and cathode coating. So basically, we do 3D sintering for both types. So about the results of cell manufacturing. As you can see here, I forgot to mention, but we only consider direct expenses for cell manufacturing, like capital expense or other non-manufacturing related work, working power or labor is not considered here, along with the capital expense, etc. So here, as you can see, the most expensive one is the fourth type, because of the price of the SCZ, basically. So as you can see also, when the scale goes up, the manufacturing cost of this all types reduces. In here, energy costs are given in detail. As you can see, firing or sintering of the cells has the biggest impact for low scale manufacturing, stated as one. But when we scale it up, as you can see, the impact lowers for sintering, and but still sintering has the most biggest contribution for all scales. This is, I just gave this graphs to you to see how the impact of material type on the cell costs. As you can see, AS stands for anode support tubes, and it is always the highest price, almost. I mean, it never changes. It stays the same for the same scale production. But when we look at the other ceramic materials, you see CSZ and HAB has the highest price at any level. So we will talk about this later. And now, when we compare to overall, as you see here, the material expenses are the highest, and when we scale it up, the impact gets better and better. So we need to develop manufacturing processes to optimize this, and you can see the materials waste rate on left bottom for the third scale of manufacturing. So as you can see, the waste rate is higher for the deep coating process. So if we could increase the deep coating efficiency, then we could lower the cell costs and further stack costs. So about the stack costs, there are several number of contributors here. This is the summary for the cost for the stack manufacturing. Stack's power is always fixed to 1 kilowatt, and this, as you can see there, depending on the individual cell performances and even at the stacks scale performances of these, number of the cells are different. So even if the cell costs went higher, we can use fewer cells. So maybe there is a way to salvage this and have a low cost stack. So this is the stack electrochemical performance chart. There are, as I mentioned, 4 different types of cells are used, and electrical efficiency is 45%. And about the stack costs. Stack costs also lowers with the increased manufacturing scale. So the change goes up to almost 45% for, I cannot distinguish it from the color, but it must be the third cell, I guess. So, no, fourth cell, sorry. So you can also see the comparison of stack material costs and overall cell cost with and without cells. The legend is, I think, has an error. It should be overall stack cost, not material cost. So without the cells, we can see that the biggest contributor is the fixation set. It's like the chassis of the stack. And then it is followed by the mounting bricks, which is also gas distribution duties it has. At low cost range, we have nickel-based sealing compounds, silver wire, silver paste for assembling the stake, and these are the costs for them. And most of the day looks insignificant compared to the other cell components, stack components, sorry. So this is a typical pie chart for cost distribution. This is from stack type 1. Manufactured at scale 2. So as you see, the major contributors are cells, and the chassis also mentioned as fixation parts. So this page shows dip coating optimization. We mentioned that dip coating can be adjusted to lower the stack prices more, stack costs. And here you can see on the left part of the page, the graph shows the waste rate of dip coating process and the cost change depending on the waste rate. So if we increase the efficiency, we can see that the cell costs goes lower and lower up to, I don't know, it's after 55% waste rates, I think it just stabilizes, and the change is insignificant. So we stop the experiments after that. So when we look at it, the stack costs and unit cell costs went down, and in detail you can see the numbers at the table over there. So if we summarize this, the change in the cost is listed here. The most change in cell scale, also for cell type 4, because again it is the most expensive material here, and at scale stack base, it is also the same. So we can further reduce the stack cost 16% approximately. So as a conclusion, we studied four different types of tubular solid oxide fuel cells at 3 different scales. Sintering is the most effective process viable by the scale up, as it has the highest energy consumption rate. Dip coating process is key to reducing the cell costs. Material costs related to dip coating can be reduced by optimization of the process further, between 7 and 16%. Thank you for your time. And if you have questions, please don't hesitate.
Thank you, Dr. Akduma. Dear first participant, if you have a question, could you please write down from the chat part? Okay, if somebody's write down a question, I will speed it. Emina Akpınar asking to you, you show that electrical efficiency of the cells 1, 2, 3 are equal. approximately equal to 45%, but cell 1 is the cheapest one. So did you get the most efficiently from cell 1 in your study?
Maybe I
Emine,
should.
yeah.
Yeah. I cannot see the question here.
Yeah,
So
nobody see that actually.
The stack efficiencies are similar. They are not equal, but approximately it was close. So we decided to assume that it is equal. So, but I couldn't understand the question. It was long. So if you could repeat it again, maybe I can answer. Or
I will repeat it. She asking, you show that electrical efficiently of the cells 1, 2, 3 are equal, approximately equal to 45%. But cell 1 is the cheapest one. So did you get the most efficiently from cell 1 in your study? This is the question.
No, I cannot remember. I checked it before, but I cannot remember right now. The fuel utilization also differs for stacks. So I didn't mention that here. Maybe we can discuss this later with our, I guess.
Yeah. Okay.
Because I need to check.
Emine Akpınar asked, maybe you can in the mail or something like that. Thank you so much, Dr. Aktuman. Another speaker, another participant, Dr. Yusuf, Bahsir Yusuf from University of Saint Malaysia. His topic is effect of annealing period on microstructural and optoelectronic properties of GO-DOP molybdenum O3 thin films produced by spray pyrolysis. Dear Dr. Yusuf, are you here?
Dear Chair, I am technic, and the speaker wants to join with a video.
Okay. Could you please share?
Yes.
Good morning, everyone. My name is Bashir from Nano Optoelectronic Research Technology Laboratory, University Science, Malaysia. I'm here before you at this very moment to present a paper titled Effect of Annealing Period on Microstructural and Optoelectronics Properties of Graphene-Doped Molybdenum Thin Film Produced by Spray Pyrolysis. Introduction. The use of molybdenum oxide as Hall selective heterojunction layer on N-type silicon has attracted the attention of researchers worldwide. The exceptional properties of the material depends on the method used to produce the films and performance related to the film's crystallinity, morphology, as well as homogeneousness. Spray pyrolysis has been shown to be an effective way for producing uniform and sizable nanofilms. The techniques has some few advantages, some of which include possible homogeneous mixing of individual precursors at the starting point. It's cost effective and a single step, as well as possible large area deposition. As such, several scientists suggested that material films properties are primarily influenced by the deposition conditions, which include annealing and as well as specified period for annealing. The period taken for the annealing may result in the composition of the films owing to the evaporation of the volatile constituents, which in turn allow the element of precursors to diffuse and react with each other to form a binary or ternary pieces. Now, methodology. Graphene-doped molybdenum film have been synthesized using 2 atomic percent graphene in 0.05 mole of molybdenum solution by spray pyrolysis at a substrate temperature of 300 plus or minus 5 degrees Celsius. The sprayed films were annealed at 400 degrees Celsius for 2 hours, 4 hours, and 6 hours respectively. The structural properties of deposited films were characterized using X-ray diffraction, Raman spectroscopy, while the morphological studies were conducted by FISM and AFM to determine the surface variation in relation to the annealing period. Meanwhile, the electrical and the IV characteristics of the produced films were analyzed using KOCAELI source meter. Now, results and discussion. For the structural analysis, as we can see from figure A, the peak related to the molybdenum, orthorhombic molybdenum films have been seen with 0.020101040 peaks and rest. The existence of 0K0, where K is equals to 2, 4, 6, confirm the production of the laminar crystal structure of molybdenum films. As we can see, the preferential growth is based on this direction, 0K0 direction. So this indicates that the preferential growth occurred in this crystal plane of 0K0. Also, we use the Willison-Hall relation to calculate the crystalline size as well as strain. The equation which is used here is beta cos theta is equals to K lambda over D plus 4 epsilon sin theta. So by comparing this equation with the equation of a straight line, the value of D, which is crystalline size, and epsilon, which is strain, can be determined. Now, the value of D and E are tabulated in the table, which also presented graphically in figure 1C. As we can also observe, the D value is increased with decreasing solution, with increasing the annealing period, having the values of 19.3 nanometer up to 39.06 nanometer. Meanwhile, the strain is increasing with increasing the crystalline size. But at 6 hours, the strain starts to decrease to 0.18 value. Raman analysis. As we can see, there is a peak related to the graphene, which is located as at 1,583 and 1,352. This band is related to the G and D graphene value. And also there is some other peaks which are related to orthorhombic structure that exist at 991, 798, 516. The peak intensity is increasing with increasing the annealing period, while there is a slightly shift at the peak position at 978, which confirm the duping and the effect of the annealing on the film properties. Morphological analysis. The morphological result has been displaced as a function of annealing period from 2 hours to 6 hours. Number A refers to the morphology of the film without annealing as deposited. B is annealed at 2 hours, C 4 hours, and D 6 hours. As we can see that the film's properties is changing with change in the annealing period. Also, the AFM analysis was displaced here. The film thickness for A, which is as deposited, is 94.8 nanometer, and the film thickness is increased with increasing the annealing period, having the value of 172.6 nanometers and 175.6 nanometer, and lastly is 235.1 nanometer, which confirm the effect of the annealing period on the film of the AFM properties. The current voltage properties was used to determine the barrier height and the ideality factor. The equation J equals to J naught exponential of QV all over N KBT minus 1 was used to find the barrier height, and the ideality factor. As we can see from the graph, the barrier height was determined and also the ideality factor was determined. Now the values of the barrier height and the ideality factor was tabulated in table here. For the first film, which is as deposited, there is a slight rectification of 168.5. After annealing, the film rectification value increased to 205.4. Then at 4 hours, it has a value of 271.3, which is the highest one. Thereafter, it starts to decrease to 100.6. And the barrier height also under dark is 0.7345 and increase with increasing the annealing period up to 0.7812. Thereafter, it decreased to 0.7457. After the films was exposed to the light illumination, the barrier height decreased. As we can see, for the 0 hours is 0.6032, and then increase with increasing the annealing period as exposed to the light, 0.6152, 0.6373, then decrease to 0.6272. And also the same thing for ideality factor. The ideality factor is increased with increasing the annealing period, but at 4 hours, we have a 2.1132, which is the lowest compared to the other ideality factors. Also, the electrical properties was conducted to determine the carrier concentration as well as resistivity of the film. As we can see from the diagram, at 0 hours, the concentration is 8.0 times 10 to the power of 19 nanometer, which now decrease by increasing the annealing period. And we have the highest concentration at 4 hours. We have the highest concentration at 4 hours. And also for the resistivity, we have the lowest resistivity at 4 hours. So therefore, 4 hours is taken to be the best for the electrical properties. In summary, or in conclusion, the molybdenum doped films were prepared by simple and easy method, which is spray pyrolysis, and characterized using tools such as XRD, Raman, FISM, AFM, and IV respectively. Material studied showed that the processing parameters have a strong effect on the material's properties. The rarely reported solution-based deposition of molybdenum doped graphene on silicon substrate via spray pyrolysis was effective and yielded a good crystalline films without the substrate being deformed. The film's developmental stages, specifically nucleation, condensations, and the subsequent growth of molybdenum doped graphene for carrier selective contact application was clearly understood by varying the annealing period after sprayed films. The films annealed at 4 hours showed a high concentration of 8.232 times 10 to the power of 19 per centimeter cube and low resistivity of 36.34 ohms centimeter. This attributed to the high rectification of 271.3 and ideality factor of 2.1132. These are some of our references.
Okay, thank you for presentation, Dr. Bahsir Yusuf. Do you have any question? Okay, if you haven't any question, we will continue with another participant. His name is T.N. Agayev from Institute of Radiation Problems, NES of Azerbaijan. Are you here? I think there is a record.
Dear Chair, I am technical staff, and
Okay.
I cannot see the speaker between the participants.
Yes.
And,
Okay, could we pass another speaker?
yes, maybe.
Okay, if he didn't hear, we can test another speaker. Okay, another speaker is Aylin Aytaç from Gazi University. Her presentation title is Nano Silver Cobalt Carbon Catalyzed for Electro-Oxidation of I don't know the name, CH3OH and MEABH4.
Methanol and sodium borohydride.
Methanol. Thank you, hocam. Thank you for the informing. Are you here? If you are ready, you can start presentation.
Okay, thank you very much. I have a video and I will be here also.
Okay.
Hi everyone. Today I'm gonna talk about carbon-supported silver catalyst for electro-oxidation of methanol and sodium borohydrate for alkaline fuel cells. As the impact of the fuel cell combustion on the climate becomes apparent, the search for the renewable efficiency, clean and safe energy sources free from the green gases is increasingly important. One of the possibilities for the complying with these requirements is to use fuel cell as a source of the energy. Fuel cells are supposed to play the significant role in power generation for stationary application, transportation, and portable electronic devices. Several years ago, we have decided to study on alkaline fuel cells due to usage of the non-noble metal catalyst and the low-cost mass production compared to the other type of the fuel cell. Non-noble catalyst, for example, nickel or silver, making alkaline fuel cells a potential low-cost technology compared to the polymer electrolyte membrane fuel cell. It is generally recognized that the oxygen reduction reaction in alkaline media is more facial than in acid media. Among the non-platinum catalysts, silver nanoparticles serves as an encouraging candidate to platinum catalyst due to its high activity and alkaline solutions for oxidation reduction reaction. Also now silver is 40 times less expensive than the platinum. This is also important point. Catalyst preparation method is very important as the physical and chemical characterization of the catalyst, electrolysis deposition method, what we use in this study. As a reduction method, recently have as widespread use in both scientific and commercial fields, use the electrolysis deposition techniques is more advantage are simpler, the other expensive and complicated nanotechnology methods. Yes, okay. The catalyst needs to have the highest possible surface area. Active carbon materials, for example, Vulcan XC22 are the common choice for supporting electrocatalyst particles in the cell because they large surface area, high electrical conductivities and porous structure. And okay. And in my presentation, I will explain to my objectives microstructural characterization of the carbon-supported silver catalyst and the electrochemical measurement of the catalyst. At the end of my presentation, I will give my conclusion about the study. And the silver deposited carbon catalyst prepared by electrolysis deposition method was examined for the redox process and electrocatalytic activities during the oxidation of the methanol and the sodium borohydrate in alkaline solution. And then the catalyst was characterized by X-ray diffraction, energy dispersed X-ray analysis, and scanning and transmission electron microscope. And also we use the electrochemical voltammetric analysis. The electrocatalytic activity of the carbon-supported silver catalyst for oxidation of methanol and sodium borohydrate in alkaline solution was investigated using some electrochemical techniques. My main objective is to make comparison and to establish the electrocatalytic oxidation of methanol and sodium borohydrate on silver deposited carbon fiber electrode for alkaline fuel cell. In the experimental study, first we synthesize nano silver catalyst using Vulcan XC2072 carbon materials as a support. We prepared the working electrode using the catalyst for the electrochemical measurement and then catalyst surface characterization and electrochemical measurements investigated. You see here the microscopy of the catalyst. The micro graph present in figure 1 and A and B display the morphology of electrodeposition of the silver obtained by SEM and TEM. It is observed from the figures that the carbon surface was deposited by silver particles, which are highly dispersed, have high multiplicity, and they are regular in shape. And you see the black point here at the TEM image. It's very clear. Okay, here in figure 2A and B. In figure 2A, the first one, display the EDX analysis that has been confirmed the presence of silver with intensity. The appearance of the carbon peak was the result of the activated carbon on which silver nanoparticles were deposited. The gold peak at around 2 kiloelectrovolt results from the grid used for the analysis. The EDX analysis has shown a strong evidence of the homogeneously dispersed silver nanocrystals at the optimum conditions. X-ray diffraction patterns of the anode catalyst, this anode catalyst employed in this study were shown in figure 2B, the second one. The major diffraction peaks of the silver nanoparticles were observed, and the Vulcan XC72 showed a typical peak of reflection of graphite around 26.34. The peak at 36, 44, 63, and 77 can be assigned reflection of face-centered cubic phase of the silver. The average particle size of the catalyst was calculated from the XRD diffraction peaks using the Schaeffer equation. Silver particle size are calculated according to the diffraction peak of the silver 111. That was found to be in the range of 3.2 nanometer. So average particle size of the silver particles is 3.2 nanometer. Okay. Typical cyclic voltammograms for the first and second oxidation reduction cycles are shown in figure 3. For Vulcan XC supported silver electrode and inner for silver bulk electrodes, respectively, the characteristic anodic and cathodic peaks X1 and Y1 and X2 and Y2 corresponds to the formation reduction of the silver oxide and silver 1 oxide phases according to the reaction 1 and 2. The observed increase of the current peaks of the cyclic voltammeter for the later cycle is caused by increase of the surface roughness during the first oxidation reduction cycle. In this case, at the potential of pre-peak Z, you see here, several monolayer of silver 1 hydroxide are formed, and above them the thicker, more porous layer of silver oxide grows. Effect of the methanol concentration on cyclic voltammograms of the catalyst with the potential sweep rate of 100 millivolt per second was investigated, and the results are presented in this figure, in figure 4. And the methanol concentration were changed from the 1 millimole to the 10 millimole. It is shown in this figure that the methanol oxidation peak current density decreases with increasing methanol concentration. Thus, the absorption of the oxidation products at the electrode surface causes the hindrance for the further oxidation. Either anodic or cathodic current decreases with increasing of the methanol concentration. It was shown that revealing the electrocatalytic deactivation of silver catalyst. If you look at the slide 10, yes, and in figure 5, the anodic current in positive sweep was proportional to the amount of sodium borohydrate, and any increase in the amount of the sodium borohydrate caused an almost proportional linear enhancement of the anodic current. So electrooxidation of sodium borohydrate on this catalyst seems to be certain. Sorry. You see here the oxidation reduction for the sodium borohydrate and methanol, and the current density of the methanol decreases with the increase in concentration to 1 molar to 10 molar. These results can be attributed to the formation of the carbonate on the surface of the catalyst. The current density of the sodium borohydrate increased with increasing of the borohydrate concentration. Maximum current density was achieved at 10 molar of the sodium borohydride concentration and remains stable. But our electrode surface area is just 1 centimeter square. The sodium borohydride oxidation shows the highest activity on carbon superwater silver electrode in alkaline medium. Thank you very much joining to my presentation. Have a nice day.
Okay, thank you, dear Professor Dr. Aylin Ataç, for nice topic. Do you have any question to our presenter? You can write it down from chat part. Okay. Thank you again for the nice topic.
Also, I want to thank you, Berna, for the contribution of our Congress. Thank you so much.
Thank you, Hocam. Thank you. Okay, another speaker. Actually, our presenter is finished, but as you know, Merve Akbayrak, we have some technical problem, and I will say again, Dr. Akbayrak, are you here, Merve?
Yes, I am here.
Okay, if you are ready, you can share your presentation.
Dear Chair, I am Teknik again.
Okay, Teknik, okay. We are waiting.
I want to help Merve to share video.
Okay.
Thank you, Hocam.
And I am happy.
Hello, everyone. I am Merve Akbayrak. Today, I am going to present you the performance of iridium nanoparticles on ceria as a catalyst for hydrogen evolution reaction in acidic medium. Hydrogen is an attractive alternative fuel and energy carriers because of its non-toxicity, high energy conversion efficiency, high abundance, high gravimetric energy density, different form of storage and production from water with no emissions. And hydrogen can be obtained from diverse resources, both renewable and non-renewable ones, such as coal gasification, natural gas, steam reforming, solar energy, wind, wave, hydro energy, and biomass. Currently, almost 90% of the hydrogen gas is produced from natural gas and liquefied petroleum gases by catalytic steam reforming or the light oil fraction with steam at high temperatures. However, these methods are always associated with the emission of greenhouse gases. On the other hand, electrochemical splitting of water with no emission is the cleanest method and plays an important role in the sustainable production of hydrogen. Water splitting is clean, efficient, and sustainable because water is the only starting molecule and the byproduct in the cycle of hydrogen economy. According to the Web of Science reports, since 1997 up to now, there is a growing interest towards the water splitting. So I want to explain what is the water splitting. Water splitting is the chemical separation of water into oxygen and hydrogen gas by applying an external voltage. At the anode compartment, oxygen production occurs by water oxidation, and at the cathode compartment, hydrogen production occurs by proton reduction. However, generation of hydrogen via electrolysis of water requires high amount of energy. To decrease energy need and improve the efficiency of the electrolysis, the cathode and anode materials, as well as the catalyst and surface materials, need to be optimized. So there are main requirements for well-performing electrocatalysts. These are low intrinsic overpotential for desired reaction, such as hydrogen or oxygen evaluation, high active surface area, which facilitates both good accessibility to the reactants and sufficient fast removal of the products from the surface. Another one is the high electrochemical conductivity, which provides pathways for electrons. Proper chemical stability is important for the compatibility with the electrolyte. Electrochemical stability, such as not being corroded at high overpotentials, and the last requirements, good mechanical stability, especially for high temperature electrolysis. When designing an electrocatalyst towards the hydrogen evaluation reaction, metal-hydrogen bond strength is a critical parameter which affects both absorption of reactants and desorption of the products. For the ideal catalysis, metal-hydrogen bond strength should be kept optimum. Volcano plot shows the metal-hydrogen absorption bond strength, which is an excellent guide in designing an efficient catalyst for hydrogen evaluation reaction. According to the Sabatier's principle, platinum is at the top of the volcano plot, and which is found to be most efficient catalyst for hydrogen evaluation reaction because of it has neither too strong nor too weak hydrogen bonding energy. However, platinum suffers from the low stability and high cost. So, rhodium and iridium metals can be an alternative to platinum. However, these metals also suffer from the high cost and low abundance. To overcome these problems, nanostructured electrocatalysts with large surface-to-volume ratio have been designed. Catalytic activity of metal nanoparticles is highly dependent on their dispersion and the particle size. So metal oxides are commonly used supporting materials. Used as a supporting materials to prevent aggregation, increase dispersion, and decrease the particle size. Also metal oxides used to increase active surface area of the metals. Ceria, titania, zirconia, hafnia, silica, and alumina are most commonly used metal oxides in the literature. For the iridium ceria synthesis, metal salts and supporting material were mixed in distilled water for 24 hours at room temperature. After the 24 hours, aqueous sodium borohydride solution was added to the slurry dropwise, and the mixture was stirred for 60 minutes to obtain dispersed iridium nanoparticles on the ceria surface. After this period, metal nanoparticles were obtained and separated from the solution via ultracentrifugation. To remove residues coming from the solution, catalyst was washed with distilled water and dried under vacuum at 60 degrees for 12 hours. The obtained catalysts were dispersed in the isopropyl by sonication for 2 hours. Then 2 microliter of the homogeneous ink was dropped onto the surface of clean glass carbon electrode. The suspension was dried on the glass carbon electrode at room temperature for 1 hour. And finally, iridium ceria modified glass carbon electrode was obtained. We prepared iridium ceria with a facile method. Then we attached the catalyst onto the glass carbon electrode by drop casting, and iridium ceria exhibits outstanding activity and stability towards the hydrogen evaluation reaction. The characterization of the iridium ceria was done by the transmission electron microscopy, and as can be understood in the figures, the highly dispersed metal nanoparticles can be achieved, and the existence of the iridium ceria and oxygen in the catalyst were confirmed by the TM-EDX analysis, and the mean particle size was calculated 2.25 nanometer from the particle size distribution histogram. Also, the crystallinity of the catalyst and supports were studied by X-ray diffraction methods. The strong and the sharp diffraction peaks in the X-ray diffraction patterns of the iridium ceria and ceria reveals that the good crystallinity of the ceria nanoparticles were preserved after impregnation of iridium nanoparticles. On the other hand, due to low iridium loading, no peaks indicating the presence of iridium nanoparticles were observed in figure 2a. Linear sweep voltammetry used to investigate the electrochemical activity of modified electrodes in 0.5 molar sulfuric acid solution at 5 millivolt per second scan rate. Control experiments were carried out under the same experimental condition, and polarization curves of the iridium ceria is given together with the linear sweep voltammograms of the bare glassy carbon electrode and ceria modified glassy carbon electrode, also commercial platinum carbon electrode. Ceria modified glassy carbon electrode and bare electrode shows no electrochemical activity for the hydrogen evolution reaction. On the other hand, iridium ceria exhibits good activity with low onset potential, low over potential, low Tafel slope, and high exchange current density values when comparing to the commercial platinum carbon catalyst. However, iridium ceria exhibits higher stability than that of the platinum carbon catalyst. So it is a promising electrocatalyst towards the hydrogen evolution reaction. The electrocatalytic stability of the iridium ceria were tested by recording the cyclic voltammogram in 0.5 molar sulfuric acid solution at a 50 millivolt per second scan rate. The results shows that there are small shifts in onset potential and over potential at 10 milliampere per centimeter square. Also the Tafel slopes after the 20,000 cyclic voltammetry cycles in acidic medium. Such shifts are commonly observed in literature even for less number of cycles. When considering the overpotential, Tafel slopes, exchange current densities, and also stabilities, iridium ceria shows superior electrocatalytic activity for the hydrogen evolution reaction as compared to the commercial platinum carbon and iridium zirconia, iridium titania, and the other reported iridium-based catalysts. Moreover, iridium ceria has more advantages over those reported catalysts, which include high temperature annealing procedures and harsh catalyst preparation conditions containing environmentally unfriendly chemical reagents. In fact, iridium ceria can be reproducibly prepared following a facile method which consists of just a simple impregnation and reduction procedure. Also, intrinsic activity was observed via the turnover, via calculating the turnover frequency values. To calculate the turnover frequency values, copper under potential deposition method was used, and in this approach, the number of active sites were calculated based on the copper stripping charge. After the calculation, iridium ceria shows higher turnover frequency values compared to the benchmark platinum carbon electrode, which indicates higher amount of hydrogen gas could be generated at the same overpotential by using iridium ceria catalyst. Also, for the electrochemical activity of the iridium ceria was also studied by electrochemical impedance spectroscopy. The charge transfer resistance is a total charge resistance for the overall rate of hydrogen evolution reaction and it decreases with increasing potential, which means electron transfer kinetic increase when the applied potential increases. Tau slope also can be acquired by using impedance spectroscopy, and the results purely reflects the charge transfer kinetic of the electrode reaction, which exclude the contribution from catalyst resistance. The tau slope of the iridium seria, 40 millivolt per decade, confirms that the Volmer-Heirowski reaction mechanism is preferable for the hydrogen evaluation reaction with iridium seria. There are also small semicircle at high frequency region, which are potential independent and arise from the contact between the catalyst surface and the base carbon electrode. Double layer capacitance is also important parameters to estimate the electrochemically active surface area. Electroactive surface area can be calculated by dividing the double layer capacitance to specific capacitance. This specific capacitance is 0.4 farad per centimeter square for the flat surface. After the calculation, we can see that the iridium seria has higher electroactive surface area than commercial platinum carbon catalyst. The higher electroactive surface area of iridium seria indicates the higher turnover frequency values and also exchange current density values. For the Faraday efficiency during the hydrogen production was also determined using iridium seria modified glass carbon electrode. It was calculated using the water displacement method via Hoffman apparatus. The volume of the evolved hydrogen gas from the water electrolysis was measured in a Hoffman electrolysis cell and followed as a function of time. The Faraday efficiency was calculated 90.9%, which is well consistent with the other catalysts reported in the literature. To conclude, we successfully impregnated iridium nanoparticles onto the seria surface by facile and environment-friendly method, and we tested for hydrogen evaluation reaction in acidic media. Iridium seria was found to be very efficient in this reaction and provides low onset potential, low over potential, and high exchange current density. Also exhibits low tau slopes. Moreover, iridium seria shows higher intrinsic electrocatalytic activity than that of the commercial platinum carbon catalyst due to the higher electroactive surface area. The electrocatalytic stability test shows that iridium seria exhibits an outstanding stability for hydrogen evaluation reaction in sulfuric acid even after 20,000 cycles without any noticeable change in the tau slope, onset, and over potential values. Considering the high stability, facile preparation method, and low iridium loading, binder-free iridium seria is a promising electrocatalyst for hydrogen evaluation reaction from water splitting. I want to thank Professor Dr. Ahmet Muhtar Önal for his support during this study. And I want to thank Professor Dr. Ayşen Yılmaz for the X-ray diffraction analysis. And I want to thank the Matthew Central Lab for the TEM and the ICP-OS analysis. And I want to thank you for your attention. If you have any question, I will be glad to answer. Also, this is my reference list.
Okay, thank you, Dr. Akbayrak.
Thank you, Hocam.
Do you have any question to Dr. Akbayrak? You can write it down from chat bars. Okay, I think there is no question, Merve. Thank you for your attention. I would like to thanks to organizing committee and chair, invited speakers, all the participant audience. It was honor to be chair of this amazing committee. I hope we will meet in the third international Hydrogen Energy Congress and exhibition will be Gazi University next year. We will meet there and with the face-to-face as well without COVID-19. Thanks again. We are close the session. Thank you.